So in this video, we're going to cover our first real application of integration, which involves this topic, displacement, and how it compares to distance and all this stuff. But before we really dive into that, we're going to revisit a topic from Calculus 1, and we're going to kind of revisit physics. And you may remember that in physics, or rather in Calculus 1, we used to have functions like x of t, and if x of t represented our position, right, maybe meters would be our unit, position at time t, right, then, we learned that if we take the derivative of this with respect to time, and we're looking at, dx dt, well, we need to remember that the letter d here literally means change in, and so this is, the change in x over the change in t. And if we remember that x is like our distance in meters, and t is some amount of time, then dx dt, which is the same thing as writing x prime of t, was also what we would call the velocity at any given time t. That's what we would call it. So this is our velocity. And we could pay attention to these units, right? Because if x is in terms of meters and t is in terms of, let's say, for instance, we can just use seconds, but it can be anything, then our unit is going to be in terms of meters per second, or something like this, right? And if we took one more derivative again, right, we do the derivative one more time, then we would end up with the second derivative with respect to t, right, which would be x double prime of t, which is v prime of t, and the change in your velocity over time is your acceleration due to time, okay? So this is acceleration at any given time t, and acceleration, the unit of acceleration, is meters per second squared, okay? And so there's a few things that we're going to cover in this video. So the first thing is that, number one, okay, if we are given that, say, x prime of t is equal to x squared plus, or excuse me, not x squared, is equal to t squared plus 3t, say. And so this is a function that represents our velocity. The question is, if I integrate this, what am I going to get? Okay. So if we have x prime of t is equal to t squared plus 3t, then what is our position function? What is our position function x of t? Okay. And in case this is confusing, remember that, x is just the name of the function. I could have called this anything. We could have written Bob of t or whatever, but x of t is very common, just like y of x is very common. So this is the question: what is our position function x of t? And the way that we can go about doing this is we're going to integrate. We're going to integrate the function t squared plus 3t with respect to what variable? Well, with respect to t, of course. And one thing to notice is, remember this, what are the units of t squared plus 3t, right? Well, if this is velocity, then the units here would be meters per second. And, well, what's the units of dt? Well, the units of dt here would be in terms of seconds. So it kind of makes sense that when we solve this thing and we get, t cubed over 3 plus 3t squared over 2 plus c, it kind of makes sense that this ends up being our x of t, because what are the units we would be left over with? Well, last time I checked, if you multiply meters over seconds times seconds, these seconds are going to cancel out, and that means that the resulting equation that we're getting is going to be in terms of meters, right? This is going to tell us our position at any time t. And, you know, just to double drive in the point, this is our position in a one-dimensional plane. So, or state of being, I should say. So, like, if this is u, and this is at x is equal to 0, what we're talking about our position, we're talking about maybe here's x is equal to 10 meters, here's maybe x is equal to -3 meters. That's what we're really talking about here, okay? So this is a one-dimensional sort of scenario when we're kind of dealing with this. Okay. Now, one thing you may notice is that we get this plus c that's popping out here. And, you know, it's not really super useful to get an equation that tells us my position at some times t if I don't exactly know what this plus c is, right? Like this equation, on the one hand, is doing kind of, I guess, what I've said, which is that it is going to be my position at some time t, but we're missing like a little bit of information, right? This plus c. And the real reason why that this is missing is, well, let's look at a graph. Let's look at an easier example. So let's go over here just for a sec as an aside, okay? Now, if you remember, okay, if I were to give you the graph of, say, let's go to y is equal to x squared, y is equal to x squared plus 1, and y is equal to x squared plus 2, for instance, each of those will give me a different parabola, right? Each of those gives me a slightly different parabola, one a little bit higher than the rest, right? And if we have these three parabolas, what do we know about the derivative of all of these? Well, the derivative of all of these, they all have the same derivative, y prime is equal to 2x. And so if I were to take this and kind of put it through its paces and try to figure out what the integral of 2x is, we've covered this concept before, we're going to get x squared plus c. And the problem is I don't know what c is. Okay, I have no idea what c is. How do I figure out which of these three graphs was I really examining, right? And another way of thinking about this is, remember, the derivative represents the slope of our function, right? And you'll notice that no matter which of these graphs that I'm looking at, whether it's x squared plus 1, or x squared plus 2, they all have the same slope. You pick any given x value, right? Let's say I pick this x value. They're all going to have the same exact slope. Well, if I draw on this one correctly, they're all going to have the same slope at that given x value. And so we need like one more bit of information to really pin down which value of c this is, right? Which graph were we talking about in the first place? And the only little bit of information that we need is we need to know what point this graph like goes through, right? If I tell you, not only do I know that the derivative is equal to 2x, right? I know that the slope is given by 2x, but I also know that the graph goes through this point. Well, I can immediately get rid of this one. I can immediately get rid of this one, and we would know for a fact that it goes through y is equal to x squared. And so it turns out that to solve for c, we need what's called, we need to know at least one point that our solution function goes through. Our solution function goes through. And we usually call this has a special name, we call this having an initial condition, you might hear called in the textbook, okay? But even though this all sounds really kind of crazy, let me just kind of just kind of paint a better picture for you, let's go back and use the example. Let's say that I know for a fact that my velocity function, x prime of t, is equal to 2t. Okay, so very similar to this. But I also know, and I know for a fact that one of the points that my solution function goes through, so let's say that at t equals 0, I know for a fact that my graph is equal to 1. So I know for a fact that the point 0, 1 is on my solution function, right? That's a point that's going to be on this graph. Well, this is really good news because now when I go and do this integral, right, I do the integral of 2t dt, and I solve this thing, and I'm going to get t squared plus c, and we're going to say this is my solution function x of t. But we also know, we also have this condition, and so we can say, okay, well, here's the solution function, but we also know that x of 0, right, that the value of my function at time 0, on the one hand, it's supposed to equal 1, and on the other hand, we would get 0 squared plus c. And so this immediately tells us, right, what does this tell us about the value of c? This immediately gives us that c has to equal 1 in this particular case, right? You may have to do a little more algebra in the future, but that basically tells me, oh, okay, so the solution to this integral is not just t squared plus c, it's going to be t squared plus 1. That this here is my actual, fully, completely solved original position function. Okay, so this is how we go about solving for those unknown constants. And the reason why I brought this up in the first place was, again, we were talking about physics. We were talking about that with using the derivative, we know how to go from the position function to velocity to acceleration. And that also means that I can now go backwards in this particular direction. Okay, and so every single time that we go backwards, a new plus c is going to show up. So for instance, if I were to start, for example, I'm not going to do the fully worked one out of this because I think it may be on your homework, and I want you all to take a stab at it. But let's say I give you that a of t is equal to t cubed minus t plus 6, and I want you to solve for the position function x of t. Well, how many integrals are we going to have to do? We're going to need to take a pit stop at v of t, our velocity. So we're going to need to do the integral of t cubed minus t plus 6 dt is equal to t to the 4th over 4 minus t squared over 2 plus 6t plus c. And then I would need to go one more and now do the integral of that, t to the 4th over 4 minus t squared over 2 plus 6t plus c dt. And now we need to complete this integral. And so we're going to get, when we add 1 to the exponent, t to the 5th divided by 5 is going to give us 20 down there. T cubed divided by 3 is going to give us a 6. 6t squared divided by 2 is going to give us a 3t squared. Then I'm going to have a c times t, and then out pops another constant. I'm going to call it plus d. And this is supposed to be, right, this is supposed to be our position function x of t. But the problem is we now have two unknown constants, right? We have, or a coefficient, right? We have the unknown constant c and the unknown constant d, which means how many different initial conditions do you think I probably need to be able to solve for both of those? I'm going to need at least 2. And so something you may see in your homework or in later problems is at the start of the problem, you would probably need to be given, right, I need at this particular step, once I solved my velocity function, right? This was v of t. Once I solve for the velocity function, I would probably need to be given some initial condition. I would need to know maybe that v of 3 is equal to 10 or something like that. Or, as it's probably going to be written, x prime of 3 is equal to 10. I would need to be given an initial condition involving the derivative. That way I could solve for c. And then at this step, in theory, I would know what c is, so I would just need to solve for d now. So then I need to be given one more initial condition. Maybe I know that x at -2 is equal to 7, right? And now I would be able to solve for the missing variable d. Okay, so that's just like a little taste of, if we want to try and solve for velocity, or if we want to try and solve for the position function, kind of depending on what we're given, we can go about doing this. We just need these initial conditions to kind of go with it. All right, so we have that concept. That's not too bad. But one thing I hope that maybe kind of crossed your brain is that in all of this, right, let's say I gave you your velocity function, v of t was equal to t squared minus t. And I said, that's my velocity function. Beforehand, when we were completing these integrals, right, the integrals, depending on exactly how we set this up, right, if this is my v of t function, it's not, but I'm just saying, like, what if it is? If we integrate v of t, right, dt, my velocity function, we are in theory getting x of t plus c, right? That's kind of what we're getting. And so now the more interesting question is, well, what happens if I integrate my velocity function over a specific interval from a to b? Like, what exactly does this give us? Okay, we know that the antiderivative of velocity is just the position function, but what does the definite integral mean, right? If I were to say that this is like t is equal to 2, and this is t is equal to 8, right? What exactly is this area under the curve? What does it represent? And we're finally starting to slowly answer that question of why we started with area under the curve in the first place. And it's really not too bad to think about. Let's take it in like a bite-sized manner first, and I think the answer is going to pop out, which, the answer is, right, if I pick a random value of t here, okay, and I talk about, what exactly does one of these little rectangles represent, well, let's see here. What this little rectangle is saying is it's saying that you are going, right? Remember that the height of this rectangle is basically our output. It's some velocity, and the width, we need to remember the width of this rectangle is like some change, here, maybe I'll use the right, is some change in time. And so my question is, what happens if you take your velocity and you multiply it by some change in time? What does this give us? And if you're not entirely sure, let me give you a simpler example. Let's say you're moving, that your velocity is 20 miles per hour, and you are going 20 miles an hour. Your dt, your change in t, your change in time, is 3 hours, right? What would this, like, what information can we get from this? Hopefully say, well, if I know I'm going 20 miles an hour and I'm doing that for a sustained 3 hours, that then if I take the 20 miles per hour and I multiply it by 3 hours, then my units will cancel and I'm going to get a total of 60 miles that I've traveled. And so each of these little rectangles represents a tiny bit of, I'm going to lie to you for a second. I'm just going to say a tiny bit of distance traveled. Okay, you're not going to realize why this is a lie right now, but just bear with me for now. So what this integral represents, what the definite integral represents, is, in this particular case, I'm going to start using a different word. I said I lied to you for a second. This is going to equal your total, what we're going to call displacement. Total displacement from time t is equal to a to t is equal to b, okay? And why am I doing this? Let me give you a slight different picture here really quick, okay? Let me give you a velocity function that goes above and below and above and below, right? So let's say this right here is my velocity function, okay? Which means up here, in this particular region here, what do we know about the value of our velocity? What is the value of our velocity at all of those points in time? Well, the velocity is going to be positive, right? And in the context of you making movement, remember that I said earlier, right, that if we're starting at some position, let's say this is 0 meters, right? And this is you. If your velocity is positive, right? Positive velocity means you have some speed going there. You're headed in this kind of direction. That's what it means to have positive velocity. But on the other side, what do we know about the velocity over here? Well, the velocity being negative there says, all right, hold on a second, after some amount of time, then you're going to start going backwards, right? And so if this shaded region here kind of represents your total distance, or excuse me, your total displacement, okay? Your total displacement, right? Well, if I just look at that top bit, that's basically going to tell me how far, right? How far I am from where I started. From where I started. Okay? But if we then say, well, let me give you just a value here to help you. Let's say this is like t is equal to 5. So if I just look at the integral from 0 to 5 of this velocity function v of t dt, that's going to give me this displacement right here, right? It's going to say, you're going to be able to solve it and get something. But if I extend this, right, maybe over here, this is t is equal to 10. And if I were to modify this integral to now be from 0 to 10, well, what do we know about our position, right? What's happening to our position in this bit right here? Well, we're moving backwards, right? And so if it just so happens that our box ends up, say, like here after 10 seconds, so let's say we just happen to be here at t is equal to 10, well, then all of this is irrelevant, right? Then our total displacement, right, our total actual bit that we've moved from where we started is actually really, really tiny, because over here, this is what we would call negative displacement, okay? And so this total answer that we're getting, if you integrate the velocity function with bounds, and you don't treat it any differently, then what we're really getting here is just our kind of like the change in our final position, right, minus, our initial position, which should kind of make a lot of sense, because if you remember what this integral represents, right, how do you execute this integral? Well, you do the antiderivative, you're going to get the position function, and you evaluate it from 0 to 10, right? What does this tell you? This says figure out your final position, compare it to your starting position, and this is going to give you the gap in those two positions. Okay. So that's fine, right? So we have this concept of displacement, and again, right, so in this particular case, our displacement would be really small. The gap in our starting and finishing position would be really small. But usually, in the real world, we don't care much about displacement. I mean, maybe we do. I take that back, right? Like, there's definitely moments when you care about that, how far you actually from where you started. But what most people really care about is they care about the total distance. And the question now is, how do we get total distance? Okay, how do we do that? And it's not so bad because, again, if we revisit this part up here in our velocity function, right? If we say, okay, the area under the curve there is going to represent this chunk of distance right here, then for the positive part, displacement is equal to distance, okay? But then we have this part over here where we backtracked, okay? The problem is that when we're doing the integral, this amount of traveling here is all coming off as negative because the integral is saying, look, you're going backwards, this is negative, and so it cancels out with our positive displacement that we experienced over here. And so what we would really need to do in order to be able to get the total distance is we would need to treat this as positively valued. That's going to do it for us, right? We had this problem in the last video when we tried to work with sine, is that the value underneath that curve, right, the integral, the area under the curve, ended up being negative, and we needed to treat it in our heads as if it was positive for it to make sense. Because once you do that, right, if we say, going back to this box example, right, if I tell you that we go to the right and we go, 20 meters to the right, and then we went to the left and we went left 17 meters, you would say your total distance is 37 meters, even though your displacement is only a positive 3 meters, right? And so we need to take this, which the integral is calculating as negative, and we need to turn it positive. And so the way we do that is we would say, if I wanted to get the total distance that we've traveled, say, along this interval from 0 to 10 in my example, we're still going to do an integral from 0 to 10. We're still going to integrate the velocity function, but the only thing is we want to make sure that this bit comes out as positive. And last time I checked, the one tool that we have in math to ensure that we get positive answers no matter what is the absolute value function, okay? And this might kind of scare you. People are kind of a little intimidated by the absolute value function, so allow me to dispel your fears. How do we tackle this? All we're going to do is we're going to split this up into two intervals. We're going to say, look, in the interval from like 0 to 5, I do not need any absolute values whatsoever because this value of my displacement, my distance that I've traveled, is already going to be positive. However, right, now I need to add in the other part. So in the integral from 5 to 10, right, if all I do is write v of t dt, we're going to run into a problem because what is the value of my velocity function in this interval over here? Well, the value of my velocity function is negative in that particular interval. And so in order for us to counteract that, we're going to slap a negative right in front of that velocity function just like so, okay? And that is going to have the same effect as if we had done the absolute value of the velocity in the first place. So remember, this thing here is already negative valued. So by putting a negative in front of it, we're going to cancel out those negatives, and it's just going to leave us with a positive. So what do I mean? Let's do one final example before we call it. So for example, so let's let v of t be equal to the sine function, sine of t dt. Okay, so I'll make a sketch for us. This should be somewhat familiar from the work that we did in the last video. But here is our sine function. So we write something like this, and it keeps going, okay? And our goal is going to be to determine our displacement, and total distance traveled. From t equals 0 to t is equal to 2 pi, okay? So again, you want to remember that this is the function v of t is equal to sine of t, that it's our velocity function. We need to remember some things about the sine graph, which is that this right here is when t is equal to 2 pi. This right here is when t is equal to pi. This is when t is equal to 0, etc. So let's think about this really quick. Okay, we're going to do this using our noggin. And if we kind of think about it, number one, if we look at our total distance / displacement in this first little chunk here, okay, so let me draw us our little line here, okay. So if we start our engines right here when t is equal to 0, let's say we are at the, let's just use miles. We're at the 0 mile marker, okay, so we're starting right here. And so we're at 0 miles when t is equal to 0. Our velocity is positive. So it looks like we're speeding up, and then our velocity, it's slowing down a bit, but we're still positive. So this box is going to experience motion in this particular direction. And now we're going to end up over here. So when t is equal to pi, we're going to be at some distance. So how do I figure out what that is? We can say, okay, well, let's do the integral from 0 to pi of sine of t dt. Okay, so if I do this, what am I going to get? I'm going to get negative cosine of t, right? The derivative of negative cosine of t is sine, evaluated from 0 to pi. And I believe if we do this, we're going to get negative cosine of pi minus what we get when we plug in 0, so negative cosine of 0. And what do we get? So cosine of pi is -1. So that's -1 with a negative becomes a +1. And then over here, cosine of 0 is 1, but the negative and the negative cancel, so we get a +1, so we get a total of 2. Okay, so what this tells us is that our total distance that we've traveled, this gap right here, is 2 miles, we'll say. And we'll say that's our units. I should have given it to us, whatever our units are, but for now, we'll just kind of roll with it. Great. So using symmetry and using our brains for a second, we would expect this to contribute another 2 miles. The only difference is that if we go backwards, right, because now our velocity is negative, so we're going this way now, our box is just going to end up directly back where we started. And so we would expect our total displacement to be 0, because this area here is a +2 and this area here is a -2. And sure enough, that's what happens, because if we remember that displacement is equal to just the integral of our velocity function dt on a given interval, so in this case from 0 to 2 pi, for us, this calculation is pretty straightforward. Integral 0 to 2 pi of sine of t dt. This we did in the last video. We got negative cosine of t evaluated from 0 to 2 pi, and this becomes negative cosine of 2 pi minus negative cosine of 0, but the value of cosine of 2 pi and the value of cosine are both just 1. So we get -1 minus a negative, which becomes a plus, so we get a +1, and that equals, sure enough, 0. And so we're getting, in this particular case, that our displacement is 0. That one makes sense, okay? So displacement ends up equaling 0, no problem. And so now for total distance, right, how do we tackle that? Well, we would expect the answer to be what? we'd expect the answer to be 4. I know that this part is contributing us to going a plus 2 miles to the right. We're going to go another 2 miles to the left. That's really what it means to go negative 2 miles, right? We're going 2 miles to the left. We would expect our answer to be 4. And so if we kind of remember the formula that we just came up with, which is that distance, total distance requires all of our movement to be positive. Distance is going to be our integral from 0 to 2 pi of the absolute value of sine of t dt. And the way that we do this, maybe I'll zoom out a bit so we can kind of see the picture while we're doing this, is we need to split this up, right? We can't integrate with the absolute value symbol there, but I can split this up into 2 integrals. I can split it up from 0 to pi, because in this particular interval right here, the value of our velocity function is positive the entire time, right? The value, all of these dots, all of these velocities are all positive there, so I don't even need the absolute value for sine of t, okay? Now, if we split up an integral like this, we would do an integral from 0 to 2 pi, but again, if I just write down sine of t dt, we're just going to get cancellation, because what do we know about the value of sine in this next interval over here? The value of sine is all going to be negative, so we're going to I also messed up my interval here. My interval is supposed to be from pi to 2 pi. Sorry about that. So what do I know about the value of sine of t on the interval from pi to 2 pi? Well, I know that all of these y values are going to be negative, so I'm going to throw in a negative right here in the front so that these negatives will cancel out and give me a positive. And so what this ends up looking like, now I'll zoom in here, is we're going to have the integral from 0 to pi of sine of t dt plus the integral from pi to 2 pi of negative sine of t dt. Again, we are throwing in this negative so that these two integrals have the same effect as integrating the absolute value of sine of t. We're making sure that all the values of sine are going to be positive. We have now achieved that. And so now we can integrate this no problem. And before we do that, we could really just rewrite this 0 to pi sine of t dt. Since this is a -1, really, I could throw it out in the front, and that minus is just going to turn this into a minus integral pi to 2 pi of sine of t dt. And we could go ahead and do these separately. So we already did this first one in just like a few moments ago. We saw that this was equal to 2. So let's run through the second one really quick. Let's evaluate this integral here. And so what we're going to get is negative cosine of t evaluated from pi to 2 pi. We're going to get negative cosine of 2 pi minus whatever we get when we plug in the other one, so negative cosine of pi. Cosine of 2 pi is equal to 1, so this first term is -1. Then we get cosine of pi, which is -1. That makes it a +1. That one makes it a -1 again, so -1. So there we go, -2. And so what we got is that this part in blue is -2, just as we anticipated. It would end up being a negative, but thankfully we took into account that this would happen by throwing in a negative of our own. And so when you subtract the -2, we will end up getting 2 plus 2, and this gives us our desired end result, which is that the total distance that we traveled ends up being 4 miles, or 4 whatever our unit is. Okay. So that's going to do it for this video. Kind of a lot of stuff here, a little bit of a blast from the past in terms of calculus, but just to kind of recap. So we wanted to recap the importance of being able to go from position to velocity to acceleration. We talked about how do you actually go about solving for this missing plus c, right? How do you actually get useful equations out of this? And it turns out we need these things called initial conditions in order to be able to do that. We need at least one initial condition per unknown constant that we have. And then the bigger question is, what is, if we're doing this, right, what does the area under the curve actually represent? And the answer is it kind of depends on the context, but in the context of integrating the velocity function, it turns out that all of this area here represents the displacement of u from like some original position. And if it's all positive or it's all negative, then your displacement is the same thing as your distance traveled. But if you have some overlap, right, if you have positive displacement and negative displacement, then displacement and distance are not the same thing, and you just need to be really careful for when you have positive displacement and when you have negative displacement, because if you do your integrals in one big giant step, they will cancel out, and while they will give you displacement, right, that's what doing the whole integral gives you, you're going to need to do the integral of the absolute value if you want to find out what the total distance traveled is. So that's going to do it for this video. Lots of stuff. We've talked about Riemann sums. We've talked about the integral. We've talked about area under the curve. And now we've given us one application to kind of be able to work with. And that's going to do it for now. So hopefully this is making sense. If not, post some questions in the discussion. Hit me up via email. Come to office hours. And I will see you around in the next video.